Hello students, in this video I will be solving modern algebra questions with the easiest of the processes applying, and after the video you can also ask me any questions as well. So G1, we are an abelian group of order 6, G2 equal to S3, and for J equal to 1, 2, Pj with the statement Gj has a unique subgroup of order 2. So are they holding or not? So here let G1 be an abelian group of order 6. So G2 equal to S3. Now since G1 is an abelian group of order 6, so G equal to cyclic. Okay, so therefore G1 has a unique subgroup of order 2. Now if G is cyclic, then D of G belong to E is a unique subgroup of D. Okay, now the statement P1 holds. Next, G2 equal to S3. So is I 12, 13, 23, 1, 2 and 3, 1, 3 and 2. So each one H2, I13, 23. These are the subgroups of this. So G has 3 subgroups of order 2. And these are there. So answer is C. So there is no unique subgroup, more than one. Options are here. Let G be the subgroup of the square. So all symmetries of the square, then the conjugate classes of G. So number of conjugate classes of given by 4 plus 6 by 2, 5. So answer is 5. 16. Consider the polynomial ring QX, the ideal QX generated by x square minus 3. So here it is. Now x square minus 3 equal to 0. So x equal to plus minus 3 does not belong to Q. So x square minus 3 is irreducible over Q. So this I is x square minus 3 is maximal ideal. In a commutative ring with unity. So it's a prime ideal. Remember that every maximal ideal is a prime ideal. Next, 17. The number of irreducible quadratic polynomials over the field of 2 elements F2. So let's take a polynomial fx equal to ax square plus bx plus c over z2. So the polynomials are x plus 1, x square plus 1, 1, x square x, and this. So there is only one irreducible quadratic form here, x square plus x plus 1. So answer is B. The number of elements in the conjugacy class of 3 cycle 2, 3, 4 in the symmetric group is 6. So in this case, the number of elements of 3 cycle S6 is given by factorial 6, factorial 3 by factorial 3. So 40 is the answer. Last question. If 0, 5 is the ring of the Gaussian integer, so the quotient is isomorphic to what? So here in this case, we can say that we have a quotient ring Z of I. 3 minus I, so 3 plus I plus 3 minus I equal to 0, 3 minus I. So 3 minus I equal to 0, so I equal to 3. So as I equal to 3, squaring both sides, I square, so minus 1 equal to 9 is coming. So 10 equal to 0. So here we can write it in this way. So 10. So Z of I given 3. So this thing is Z, 10Z. So D is the answer.